at Chevron, class of 2019 from A&M. I've got a pretty extensive background in geophysical research, specifically near surface geophysics. Did quite a bit of research conferences going over geophysics research. And after I graduated, I got a job with the startup, worked as a data scientist and as a developer, worked a little bit in the field as a geophysicist, and realized that I did not want to work in the field for the rest of my life. So I got some proper certifications as a data scientist through IBM and from Google, and some TensorFlow certifications. And since then, I've had the great privilege of being able to work for Chevron as a GIS developer. For those of you that aren't familiar with what GIS stands for, that's Geographic Information Systems or Services, depending on what definition you're looking at. So essentially, I build web and mobile platforms for all of our different field engineers and field workers in Chevron, for them to view different arrays and assortments of data. So I work very closely with data engineers and with data scientists, and I'm looking to see how I could potentially use some of the things that I'm going to talk about today, how I can incorporate that to provide Chevron with additional value in the future. Y'all have any questions? Nope. Cool.
I think like for Chevron, you guys are using a lot of data analytics, right? It's like super important right now. So can you tell me like how important it is? Like how, I mean, I know that is a really broad question, but like how the company is advancing in the current moment in the oil and gas industry using data analytics. I mean, what are the advantages that you guys are seeing by the use of data analytics? Are you guys like saving some capital investments by the use of data analytics? How important it is right now, this for Chevron?
Yeah, so what we can do with that is I have a designated period of time for like 15 to 20 minutes at the end of the presentation, and we can definitely dive into that a little bit more if that's okay.
Right, yes. Nice.
Awesome. I will put that down.
Yeah, in the meantime, yeah, just write your questions in the chat, and we'll have like, 15 minutes at the end reserved for Q&A.
Perfect. Awesome. No, that's a great question, though. I really appreciate that. That's definitely something worth noting. So this class is made to be as simple, bare bones as possible, in an attempt to make neural networks more of an approachable subject. Something that I've seen a lot with a math minor, with a rich math background, but also being able to have a lot of field experience, there tends to be a huge knowledge gap between what people think that they understand and what they actually understand. And through all of this different technology jargon and big buzzwords, the underlying mathematical components of complex components of AI and machine learning that can kind of get diluted and lost. So this is going to be really simple. If this is not up to your, if you are really familiar with neural networks and you're looking for a little bit more, I could definitely direct you to some more resources, and I'm sure Will could do the exact same as well. So with that, we'll dive in and get started. So, very simply put, I'm sure a lot of y'all have already been in different classes talking about, like what is machine learning? And machine learning, simply put, is being able to have algorithms that are able to learn from data without having to explicitly write any type of rules-based programming. And what that allows us to do is to really crack open a whole new set of value to both individuals, so students, researchers, but also on an enterprise level, we're able to find patterns, and we're able to advance our internal analytics through a quantum leap of technology by implementing machine learning rather than doing simple rules-based programming. So on that, we talked about artificial intelligence, machine learning, and what this lab is going to cover, neural networks. So these are all different subsections of each other. So Neural nets, that's a subsection of machine learning, which is a subsection of artificial intelligence. Again, I'm just going to be kind of going through like broad different definitions here. If this is all repetitive to you, then I do apologize. You know, as I said, AI is a branch of computer science that simulates intelligent and adaptive behavior in computers. That's the broad terminology, and from there you can have, you know, huge different trees of knowledge, different subfields within AI. Machine learning, as I described earlier, it's the ability for patterns to be detected without having to explicitly program them. Supervised learning is being able to help direct the algorithm by labeling training data, being able to refine and be able to produce more accurate and more precise results, and to be able to iterate. You'll see through this whole presentation, iteration is something that is critical for the success of a good data science project. One final definition here. So a densely connected feed-forward neural network, so that's what we'll be focusing on here, is, sorry, totally lost my train of thought. It has the ability to capture complex relationships with many layers of data, talking about, so for a deep neural network, we're looking at, so take pictures, for example. You have different pixel by pixel presentations. How do those slight variations in pixels, how can those be understood at a much higher level to produce more predictive analytics? So a perfect application of this, and something that we see a lot in this field now is, you know, you have automation, so things like self-driving cars, being able to predict and understand what are the physical shapes being presented in front of various sensors. That is a task specifically set out for deep neural networks. But kind of moving beyond all the different high-level classifications, looking at the building blocks. So when we're talking about an artificial neuron, this is the most simple, rudimentary form of our neural network. So we have an assembly of different input nodes. So our inputs are here. We have connections and edges, which have a weighted sum, your transfer and activation function, your output node, and then biases. And we'll get into biases a little bit more. So building from this simple neuron, we can have a network of neurons. So like I said, we have our various weights, we have our hidden layers, and our input layer. So that this first layer that we have here, it should be number of nodes, not nudes, my apologies. Let me fix that really quick. Nodes, cool. So our number of nodes, so that's going to be different predictors. So if we were to put this in a practical example, if we were to have different inputs that would predict whether or not we get a good grade on our test. So our output layer could potentially be what is the grade of our test. Our different input layers would be how late did I stay up the night before? That's one to include. Do I exercise every day, you know, or what is the frequency or intensity of my exercise? And then the third one, we could say, how much caffeine and sugar have I consumed in the past 48 hours? So with those different inputs, with those different nodes, we have that pass through a hidden layer, and a hidden layer attempts to learn, it attempts to formulate all of our different inputs and help to find patterns in a much more efficient, much more effective manner. If we were to add multiple hidden layers, the theoretical assumption, and this is yet to be completely proven out, but we've seen in practice that by adding additional hidden layers, we're able to expedite the learning process. There are some pitfalls associated with that, but we can touch on that a little bit later. And then the weights themselves that interact between the various input, hidden, and output layers, those are initialized randomly, and that gives us a better chance to use backwards propagation, which we'll touch on in just a second. So for our neural networks, there are three main topics associated with the actual flow of our learning process. So forward propagation is the process in which the data passes from the input layer to the various hidden layers to the eventual output layer. This happens through a set of, if y'all are familiar with linear algebra or vector algebra, a dot product process. You have these consistent dot product functions going in and out between the input layer into the different hidden layers. The backwards propagation, so that is the process of fine-tuning through different optimization and loss functions. We're able to see where did our iterative process stumble a little bit? How can we tweak our error rate based off of our loss? And then activation functions, which are applied to the value of each node after the node value has been calculated. So after the node value has been calculated, and these functions are critical in being able to capture any type of non-linearities in data, and it provides a lot of different room for testing and for tweaking the actual application. Whenever we're assembling neural networks, and because there can be a different activation function within each or after each node, it provides a lot of different wiggle room in which either an AI engineer or a data scientist, they can spend a lot of time working through this math, trying to figure out which activation function can produce an optimal learning result. So before I move into the actual programming component of it, Will, do you think it would be a good time to kind of stop and take questions really quick?
Yeah, we do have one question.
Okay.
I think it's like not like just like a general question. So,
Okay.
what is the future of geologists with data science skills given the low oil price situation? Because I've heard many geologists and data science are laid off from the company.
Sure. So Will, do we want to, I have a feeling that a few more people are going to be asking some more career specific questions.
Yeah, I think
do we want to increase our time allocation towards the end of the presentation by 5 or 10 minutes or so? Give maybe 20 minutes for Q&A, 25 minutes? Cool,
sure.
Perfect. Let's do that. Awesome. Yeah. And if y'all have any more specific career related questions, I'd be more than happy to help. I was a recruiter for the College of Geoscience the whole time I was at A&M, and I'd be happy to answer questions or help out in any way that I can. Really good stuff. So let's do some actual coding. So let's start with the basics. I'll give y'all just a second. I need to grab some water because my mouth is getting super dry. While I'm grabbing some water, y'all go ahead and get your notebooks pulled up, and I will be back in just a second. Alrighty, appreciate it, y'all. Thanks for being flexible. So I'm assuming that most of y'all have your labs pulled up. So let's go ahead and start with simple stuff. We're going to import TensorFlow, import NumPy as well. That way we can put together really simple data frames that we can begin to kind of work through this process on. So I'll go ahead and run this one first. All right, so we have imported our libraries, and we're going to begin to construct one of the most simple neural networks that we can. So our neural network is going to have one layer which contains one neuron. The input shape is just one value. So the word dense in this instance is going to define a layer of connected neurons. So the verbiage here relates specifically to a layer of different connected neurons. So we're going to begin to assemble our model. We're going to call Keras. Sorry, dogs are barking. Let me close my door really quick. All right. So let's kind of like review a little bit on loss function, optimizer. These are some other topics affiliated with neural networks. So our loss function is going to be the measured guess of how well our answers, which we know are correct, how well those, I'm doing a poor job of explaining this. So I'm just going to read off. Measures the guessed answer against the known correct answer, and is able to predict in the future how well or how poorly that algorithm performed. The optimizer is going to be based off of the loss function. So depending on how well or how poorly the loss function performed, the optimizer will try to minimize the loss. This process of going back with the loss function and the optimizer working together, that goes through a repeated number of different epochs, which I'll demonstrate in just a second. This lab will use mean squared error for our loss function and gradient descent for our optimizer. For those of you that do have a math or a statistics or a CS background, those are going to be pretty familiar terms for you. Mean squared error is going to be able to tell you how far away your prediction is from it. It's going to, mean squared error is going to allow for the best possible fit of your data. The squared portion of that is going to ensure that your error is always positive. Gradient descent is going to be the process of, oh shoot, I should have included a graphic of this, I apologize. This is difficult to explain just right off the bat. So gradient descent, moving down a collection of slopes to minimize error. So whenever we're talking about, well, I think one of the most common graphs that we see for gradient descent is the ability for a data point to be able to, I'll pull this up at the end. Let me make a note of this really quick. I do apologize. Gradient descent.
Oh, we do have like a technical question.
Okay.
Yeah, so are activation functions basically producing different models? And is the optimal function determined by trial and error?
Yes, yes to both. So it is produced by trial and error. So another thing which I did not include in this slide, but is critical. So there is a lot of literature out there regarding which different activation function, which one will work best for your specific case study. So if you're doing a regression study versus a classification neural network, you're definitely going to want to explore. ReLU is super, it's super popular. I haven't had too much experience with max out, or I mean, sigmoid is really common as well from a mathematical perspective. So it is a lot of trial and error. Was there anything else associated with that I need to touch on, Will?
I think that's all for the question.
Cool. Okay. All right. So and like I said, once you're comfortable with the basics of your optimizer and your loss function, you're really going to be able to kind of open up this window of opportunity and being able to explore different optimizers, different loss functions, and the different results that those can produce. So for this baby example, in this instance, we're going to be using 6 different X's and 6 Y's. The relationship between our X's and Y's can be defined as the function of Y equals 2X minus 1. Super straightforward. We're going to call our NumPy library to create our data arrays. So I have all of these already created. We're going to make sure that these are inputted as floats to make sure that we have no errors. And now we're going to actually train our neural network. You can see that this is, you know, kind of like demystifying neural networks. This is not a difficult process. We're simply putting together a NumPy array, describing a function, having values, but you will notice that I did not input Y equals 2X minus 1 anywhere in my line of code. I simply had a input and an output, and we're going to let the neural network do the work and see if it can figure out which equation is most closely associated with the results that we have. So we're going to, with our model that we called earlier, we're going to call the model.fit function. And this loop of epochs will measure how good or bad our loss function is, and then we'll use our optimizer to make another guess. So we're going to run this for 500 epochs. And you'll see up at the top how quickly, oops. So we start off, loss is about 43.4395, and we rapidly are able to drop down. I think we got this down to, I mean, let's see. Yeah, 10 to the 5th. So, so now we're going to test our neural network itself. So now that our model has been trained, and we've been able to, our model has been able to establish a relationship between X and Y, we can use the model.predict method to figure out the output of Y for a previously unknown X. So we did not have 10 in there at all, so we'll run it. So we might have assumed that this would be exactly 19 because 2X minus 1 would give us exactly 19, but it wound up being a little bit underneath that. Why do y'all think that would be the case? Y'all can answer this if you'd like, or we can chat about it too. Rounding error, yep. So rounding error would be part of it, but also we have to consider that whenever we're constructing these equations, it's not going to be a perfect fit. So although we do have, you know, you have to keep in mind, these are 6 inputs, 6 outputs, and although they're being run for a series of 500 epochs, you know, is that really a sufficient amount of inputs and outputs to be able to have an airtight estimation? Probably not. If we had a much larger data set, probably, you know, like let's say in the thousands or 10,000s, that might be a little bit overkill for Y equals 2X minus 1, but that would be more of a sufficient training array for this to be then trained and then tested. So it all has to do, you know, 18.977 is close, but the more inputs and outputs that we have to train, the better our final prediction could and would be. So we're going to put this into practical sense. So let's say that I'm trying to figure out, I'm looking to buy a house in River Oaks in Houston, and I would like to figure out the house costs based off of my equation. So a house costs $50,000 to start, and then per bedroom we have an increase of $50,000. So 1 bedroom house would cost $100,000, 2 would be $150,000, etc. How would we create a neural network that learns this relationship so that it could predict a 7-bedroom house? So I could predict that a 7-bedroom house costs approximately $400,000. So we're going to go through the exact same process, really similar to what we just did in the above example. We're going to import TensorFlow, import NumPy. from the TensorFlow import, we're going to additionally import Keras. These models can then be run. We're still going to do simple one neuron, one input, one output. Our optimizer is going to be gradient descent. Loss is going to be the mean squared error. And then let's use, so for these examples, we're going to have our numbers scaled down a little bit to where our answers are going to be in hundreds of thousands. Because if we were to type in, 100,000, 200,000, that would get messy really quick. So for the sake of being concise, we'll run it as is. So we're going to run this for 1,000 epochs. Give it a little bit more time to mature between the model or within the model with the optimizer and with the loss function. Train a little bit more. And then to predict our final outcome, so our prediction, we have just over $400,000. So remember, this is in hundreds of thousands. So this is again, if you are an expert in neural networks, this is probably one of the most underwhelming labs you'll ever see in your entire life. But for those of you that are brand new to this, I know whenever I worked last year at the Datathon, I knew some people that were trying to figure out how to do a Hello World app in Python. They were simply trying to print Hello World, and they were having some difficulties with that. So this is meant to be approachable, non-judgmental, and just a really straightforward way to kind of demonstrate the simple overlaying principles of what we're talking about with neural networks. I shared this lab with Josiah before I actually presented it, and his recommendation to me, and I'm glad I took it, was to include a little bit more about, include some more graphics, include a little bit more about activation functions, and I'm super glad that I did that because I still have 30 minutes left. So I figured that y'all might be interested in doing a little bit more heavy lifting with coding. So Josiah put together this excellent lab, which I would highly recommend checking out on his GitHub repository. It's a classification lab using sklearn. Definitely recommend it. I thought about including it in on this lab, but I was not sure how good I'd be doing on time, and we flew through that because I talk 1,000 miles an hour. Does anybody have any other questions related to the specific content of the lab? And then we can kind of move on from there.
Yeah, we have one question.
Okay.
Could gradient descent be described as a linearization of what the gradient is tangent to?
That's a good question. I wouldn't be able to answer that right off the bat. Will, could you give any input on that? My definitions for that would be rusty.
I wouldn't count on me. I'm sorry.
Oh, cool. That makes two of us. So what was the specific question? We can explore that together.
Mm-hmm. Yeah, I have that question saved.
Okay, cool. Does anybody else have any other questions that we can kind of get into the ones that were addressed at the beginning of the call?
Yeah, we have a question. Does a model fit automatically do the back propagation as well?
By the way that this is designed, yes. And that's what makes these libraries so powerful is so you don't need to do anything with the back propagation. The process of the back propagation itself is going to be through the actual optimization and loss function. So as we are iterating and attempting to build connections, and granted, we did not have multiple inputs. We simply had like one set of inputs, one set of outputs. We had simple integers like what is the price of a house? It costs this much in this area. If we are sorry, I totally lost my train of thought. totally lost my train of thought. Awesome. Talking
There's
about
some
models.
more technical questions if you
Sure.
okay. Can you have you always used the TF for neural networks, or have you hard coded the model before?
I have never hard coded the model before. Like I said, I am by no means the AI expert of the world. My day-to-day usage of it at Chevron is slim to none at best. But I do understand the systems in which the workflow operates, and I think that that's where I can kind of provide value, is by breaking it down and simplifying it as much as possible. Some other really popular libraries, Keras, PyTorch is another one that's really popular. Building these models from scratch is something that I've seen lots of different PhD students and even some master students kind of touch on, but it gets really technical really quickly, and that's usually reserved for some of the more cutting edge applications of neural networks.
And do you want to keep on presenting, or do you want to answer more questions?
Yeah, I'd be happy to answer more questions. I'm done with my presentation. So if people would like to, so if people would like to enjoy the rest of their Saturday, they're more than welcome to do that. I appreciate those of you that listened in on a Saturday evening. Please feel free to check out Josiah's lab, but I would be happy to talk shop about other things that I might have missed that you think are like worth noting in the lab that I put together, or if you had any specific questions related to what neural networks are, or how you could potentially use them in work, I'd be happy to answer those questions.
Yeah, we do have a few more questions.
Yeah.
So can you explain how to implement a neural network with more hidden layers and different types of layers involving pooling, etc.?
Yep. So that is something that's a great question. So that is something that Josiah does cover in this lab. And then if you look back into his, if you go up a level from the one that I currently have designated in the URL in his intro neural networks, he does get into pooling and other different components. Adding in different inputs, adding in additional hidden layers is going to make for a much more complex neural network. And again, those are some of the applications that companies are really interested in, particularly for pricing estimation and et cetera. But I do not have any of that included on the lab, and I wouldn't want to misspeak not having any of that information readily put in front of y'all.
And we do have a question that's really similar to that, kind of going off of that. How would you create additional layers, and is there any rule of thumb you have for how many layers you would ideally need?
So that's really going to be dependent upon the problem that you try to solve. So I'm sure, as y'all can see, I'm definitely, as I've said, I'm not the neural network expert, but to me, and the thing that I talk to different business leaders about a lot is, whenever it comes to a data science project, you have the mathematical and the programming component of it, where we talk about the different theoretical aspects of it and how do we produce the best results possible. But at the end of the day, every single data science project, when we're talking about an actual job, or if we're trying to implement this in a research paper or any type of practical real world application of these things, we have to understand what goal, what is the purpose of the project that we are assembling. So if we think that having 100 different inputs would really help to answer one particular question, well, we're going to want to have those inputs. Looking at this from an agile methodology perspective, we're going, if you are familiar with agile production, we're going to want to start with the bare minimum, have an MVP of our different input layers. So what are the bare bones things that we need in order to generate our output layer? From there, we can begin to make tweaks, add in additional input layers, see if we're able to get better results with that. But a lot of this is going to be trial and error, especially if you're taking on a new project with things that haven't been done before. One thing that I will add to that is that's what's so great about having different platforms like, like this Datathon, or medium.com is another great, it's another great resource for different data science projects that have been put together, practical applications of this technology that are posted completely open source. It provides you the opportunity to be able to see what other examples have people done with this technology. How can you apply specific components of that to the problems that you're trying to solve? But in this is a very disruptive day and age with the technology that we have. So if you're looking for new or unique opportunities to use neural networks, it might require a little bit more elbow grease and a little bit more trial and error to get that desired prediction output. Does that help? I know that was long-winded, so.
Yeah, and we have one more technical question.
Cool.
So, yeah, say we have 5 years of data. Would I use the same method of training data for predicting a 5-year future models, or how would I do that? Or also, how would I do that?
So let me make sure that I understand the problem correctly. So we're saying that we have 5 years worth of historical data, and we're trying to make predictions in the future over 5 years of data that we have stored in some type of repository. Is that correct?
Yes.
Okay. Yep. So again, that's really going to depend on, that's a super broad question. It really depends on the answer that we're trying to solve. So let's say, we have 5 years worth of data. It depends on, and this is where we kind of have to step back again for a second and say, what is the application of this data science technology? This is where we really rely on SMEs, or subject matter experts, to say, okay, with this knowledge background, is having 5 years worth of historical data, are there going to be any discrepancies that we need to notate? So let's say we're talking about hospital admissions. Well, if you were to talk about hospital admissions from the year 2017 to 2022, well, there's probably going to be something really crazy going on in 2020, right? Whereas if we're talking about the stock of tires in a repair shop, that's probably going to stay pretty consistent within a 5-year time span. So time is one of those tricky variables that can really, really skew your data. And that's where, again, before we get into any type of optimization, loss functions, any type of heavy research into our activation functions, we need to understand fundamentally what problem are we trying to solve, and what discrepancies might be within our individual input layers.
Cool. And we have like a general question that I've hinted earlier. What is the future of geologists with data science knowledge, given the low oil price situation? I heard many geologists and data scientists have been laid off.
Okay. Cool. Yeah. So I can answer that. So one thing that I would recommend, if we do have anybody that's in the geosciences in particular, I would 100% recommend that you look into some online learning resources. All of my data science background was either self-taught, like on my own through doing different YouTube videos, labs, things that I found on Medium, in addition to getting professional certificates through IBM and from Google. They cost me maybe $100 total and took me 4 to 6 months to do. But it instantly makes your resume as bulletproof as it can possibly be. Speaking personally, so I was a geophysicist. I graduated a year early. and I really had a difficult time finding a job. I applied to, so I was supposed to get my PhD, funding fell through, and I had 2 months to find a job. I applied to about 175 different jobs, and this is right around the time that oil tanked. So people were really reluctant to hire, and they were especially reluctant to hire an undergraduate geophysicist without a master's degree or a PhD. So being able to take really like to be able to take the opportunity into my own hands and say, you know what, I know with my foundational math background, so all the different engineering calculus, I've did linear algebra, which is, you know, that is the godfather of any type of machine learning or AI. Having the competency in those subjects, I was able to pivot and apply it immediately to data science and to ML. Specifically for the oil and gas industry, nobody is going to be there. It's going to be impossible to say like, oh, like if you get this skill set, there's no way that you're going to be let go, because, you know, as we've seen in this year, you know, really crazy circumstances can happen. I will say though that if you are an excellent geologist with a master's or a PhD, or if you're a good geologist with excellent application of data science principles, I would say on my own, this is Nick Smart's professional opinion, I think that those geophysicists and geologists that can apply their knowledge into data science scenarios, they are 10 times more valuable, not because they have not because they have some sort of superpower with data science or with ML, but the way that they're able to view problems, to be able to view opportunities. It's like what I said earlier about kind of like broadening your horizons. If you're able to be a subject matter expert in geology or geophysics and then apply your knowledge background, if you're able to say, I as a geologist know these different input layers, and I can tell you that there's something wrong with our data, that can save hundreds of thousands, if not millions of dollars looking to build out really complex deep neural nets, all because there was some type of mathematical error before the data even came into the system itself. So that's definitely something worth considering. If we're talking about specific applications of AI and data science, that's another thing where oil and gas companies are really starting to speed up their generation of ideas and of potential value. I've seen compared to other industries, oil and gas historically they're a little bit slow to the ball game whenever it comes to adoption of new technologies. I think that COVID has definitely caused some of the better companies to be able to pivot and adapt more quickly, while others that are not willing to adopt some of this more forward-thinking processes, they're kind of left in the dust because the practical applications of this, being able to predict, so predictive maintenance is a really big one. You see a lot of different case studies of companies being able to shave, you know, you're talking several thousands, if not millions of dollars off of their OpEx, off of their operational expenses, because they're able to do predictive maintenance algorithms on different types of equipment that they have. We're talking about wellheads, we're talking about different drill bits, being able to predict when that drill bit could potentially crack, depending on the stress of the bit, depending on the temperature of the surrounding area, how well is it being maintained. These are all things that we can input, but again, it all starts with the subject matter expert. If you don't have that background knowledge, you're not able to apply that to a data science or to an AI environment. Does that help?
Yeah, the person who asked the question says yes. So
cool.
Yeah,
Awesome.
great.
All right, cool. Yeah, and also if anybody has any other questions, or if you'd like to hear more about my background, or just kind of want to talk about stuff, You're more than welcome to reach out to me on LinkedIn. It should be easy to find me, Nick Smart with Chevron. So please feel free to reach out to me for any questions that you might have related to career advice or anything else like that. I'd be happy to help any way that I can. Let's see. And then there was another question about Chevron and analytics. Is that right? Could you repeat that question? Actually, I want to make sure that I answer that properly for you.
Yeah, actually, the question is more like during like these times of low oil prices and all of that, I see like Chevron is one of the oil companies that is most spending money with data analytics. And I would like to see how the company is maybe saving capital expenses due to the application of data analytics. How is it going with the company?
So your question is using data analytics as a business enabler. How could and how can companies reduce their overall expenses by adopting like analytic techniques? Is that correct?
Right, but I would like to know more like how Chevron is doing this. If you can talk about it.
Yeah, so unfortunately, I can't speak to too many specifics about how Chevron is doing that. I can speak broadly within the industry. Some of the examples that I gave just a few minutes ago about wellhead and drill bit breakage predictions, any type of predictive maintenance in regards to equipment is big. Another thing, so the startup company that I used to work for, they're called Source Water, and the project that I helped to kind of put together was being able to predict where frac ponds. So whenever you are conducting a frac in West Texas, you need to have a lot of water readily available to be able to initiate the frac, flush after the fracture has begun, and then hopefully recycle that water to extract any type of precious minerals other than crude that you might have extracted. The idea that I put forth and helped to generate was to be able to use satellite imagery to assemble a predictive analytics engine to see, based off of road marks, based off of construction traffic, could we predict where a new frac pond, so a standing body of water with this frac fluid, where it could be built, in the hopes of being able to help to commoditize and to help transition the purchase and acquisition of Permian fracking water. So that's one specific example that I worked on. I can speak to that because that's a product that's been out there for, I want to say, 2 or 3 years now. I can't speak to anything specifically related with what I do at Chevron, but some other examples would definitely be, so you've got predictive maintenance for equipment, for workers as well. So looking at it from a health and safety perspective, that's something that a lot of whenever I first got started in oil and gas, I didn't really think, health and safety, it's not really, you don't take a class on health and safety policies, but that's another really critical application of this technology as well, is how can we ensure that our workers are going to be safe? How long have they been on the job? Are they working 60-hour shifts while they're trying to complete a drill? Are they well rested? Are they well fed? How much have they moved? If we're able to do kind of like location-based tracking, that there are tons of the applications of this technology is limitless. It's as I said earlier, it's really how well do we understand the business problem that we're trying to solve. One cautionary note that I would make, and something that I've seen from in lots of different different articles and different publications, is whenever a group or a company has a solution and looks for a problem, that is never ever as effective as starting with a problem and then working from scratch attempting to build a solution. But by all means, you can look at different solutions that have been implemented. what other industry leaders have done, what other and looking outside of your immediate industry. There's been a lot of influence from oil and gas there's been a lot of influence from medical fields, from big technology companies like Microsoft and like Amazon, that oil and gas operators have attempted to try to mirror and to provide in their day-to-day operations. So it really does start with the overall ability of being able to figure out what is going to provide the most value.
Thank you.